What I'm going to do in this part of the lecture is look at some important refinements to the measurement of gross domestic product, aspects of gross domestic product that we are also going to use quite extensively during our course. The first of these is a measurement issue, and it's a very, very important measurement issue. And I want to take the following example. I'm going to suppose in a particular economy there are only two commodities that are produced, cheese and wine. What I'm going to explain here will generalise to a real world where there are many thousands, perhaps millions of commodities. But I can make my point in this simple example with just cheese and wine. And I want to look at the calculation of GDP over four distinct periods, 2009, 2010, 2011 and 2012. And I'm going to focus on the expenditure interpretation of GDP, but obviously it doesn't really matter that much. When I say expenditure, I could just as equally have said production or income. So let me just fill in this table a little bit. We'll suppose there are 100 kilos of cheese produced in 2009. The price is 15. The value is simply price times quantity. Now, I'm going to introduce a little bit of terminology here. When I make a calculation like that, I'm talking about what is known as the current value. What I mean by current value is that I'm taking the quantity in that period and valuing it at that period's price. So that value of 1500 is the current value of cheese in the sense that we've taken the 2009 quantity and valued it at the 2009 price. You'll see why that's important shortly. We'll put in some numbers for wine, 25, 22, and a value of 550, and we'll just fill in the rest. Total GDP in 2009 will be the sum of those two values. Think of that as the final expenditure on cheese and wine over that year in this economy. We'll just make up some numbers for the following years. So we have a series of numbers for GDP, one for each of those years. And those numbers are going to be given a special name. When we calculate GDP in this way, we're going to refer to that as the economy's nominal GDP. Nominal GDP equals the sum for each commodity in the economy. Now in this case we only have two. The sum of the current price times the current quantity. Now remember, by current, I mean that for each particular year, I've valued the quantities in that year by the price that was current in that year. So this nominal GDP in 2009 is reflecting the prices in 2009. Nominal GDP in 2010 reflects the prices in 2010. Now, doing this exercise is actually quite significant in a sort of very fundamental way. Let me just highlight what we're doing here. We're using those current prices to value the quantities in each year. One way of thinking about what's happening here is we're using those current prices to, let's call it, weight the commodities each year. You can think about what's going on here as follows. For a given quantity, commodities with a higher price will therefore be given a higher weight in the calculation of GDP. So let me just repeat that. For a given quantity, commodities with a higher price will receive a larger weight in the calculation of GDP. That's actually not a trivial statement. It reflects one of the core beliefs that economists have about market economies. That is that the price of a commodity, in some meaningful fundamental sense, reflects the social value of the resources that comprise that commodity. The whole point about a market economy, when it functions well, is that prices reflect the true social value of goods and services. So when we say we are going to weight commodities according to their current price, so that for given quantities, commodities with a higher price receive a higher weight, is actually saying something about our belief in the legitimacy of a market economy to deliver prices that in some real sense reflect true social values. So resources that are valued highly by society as reflected in a high price are going to receive a high weight in the calculation of GDP. So that sounds like a pretty good thing, but there is one drawback to this current price calculation, this nominal GDP. And I'll take another example to illustrate this quite dramatically. Let's just use apples and oranges with clearly made up numbers. Now look carefully at that table. You'll notice a few things. First of all, for both apples and oranges, the quantities are increasing through time. Secondly, for both apples and oranges, the prices are decreasing through time. And the third thing is, if you do the nominal GDP calculation, exactly as we have done in the previous slide, you'll see that nominal GDP, now remember I'm going to use the letter Y as my shorthand for nominal GDP, is trending down. Now, why is this a problem? It's a problem because when you see nominal GDP trending in this way, in this case it's trending down, you're never exactly sure what it is you're seeing. Is it because the price is changing? Or is it because the quantity is changing? Is it being driven by price? Is it being driven by quantity? If all you were looking at was nominal GDP, how would you know? Here, nominal GDP is falling, but it's disguising the fact that quantities are increasing. So nominal GDP has this disadvantage that when we look at what's happening to nominal GDP, we actually aren't really sure what's happening at all. Is it prices changing? Is it quantities changing? Perhaps they're both changing. Perhaps, as in this case, one is going up, one is going down. Who knows what's going on? And so using nominal GDP as an indicator of economic activity can be problematic. We simply don't always know how to interpret it. There is a solution, however, to this. The solution is to not use nominal GDP, but to use another concept, a concept known as real GDP. The way real GDP works as follows. We'll take the same apples and oranges example, but I'm going to choose one particular year. It doesn't actually matter which year you choose. I'm just going to choose 2009, and I'm going to declare that to be the base period. And I'm going to declare the prices that existed in that base period to be the base prices. In this case, for apples, it's 10. For oranges, it's 15. And what I'm going to do in my calculation of real GDP is, as we progress through time to 2010, 2011 and 2012, I'm going to value the quantity of apples in each of those years using that fixed base price. And for oranges, I'm going to value the quantity of oranges as we go forward in time using that fixed base price. And I've done that calculation in the table for you, and you'll note that what we have with our real GDP is now an upward trend. And why we have that is we have, in this calculation, eliminated the effect of price changes. We must have eliminated the effect of price changes because we've held the price fixed at its base value throughout all other periods. Which means when we look at what is happening to real GDP, we know by definition that a change in real GDP must be reflecting a change in quantity, because price and price changes can have no role. Now, for most purposes, macroeconomists are interested in real GDP because ultimately we're interested in the quantities of goods and services that are available to the economy, that are being produced in the economy. So nearly always in economic analysis, it's real GDP that we're going to be focusing on. And we're going to focus on it because when we see real GDP change, we know we are looking at changes in quantities. We don't have to worry about whether we're looking at price changes or quantity changes or some combination of the both. It has to be quantity change. There is one aspect to this real GDP calculation I want you to be aware of, one potential problem with the technique I described on the previous slide. So when we use those base period prices and we use those prices to value goods and services for all subsequent periods, what we're doing is we're freezing the price weights at their base values. You'll recall when we talked about nominal GDP, about how commodities in the economy are weighted according to their price, and I argued, well, that was actually a pretty good thing as long as you accept that prices are a legitimate measure of the social value of commodities. But of course, the social value of different commodities can change through time for a variety of reasons. By using base prices, what we're essentially saying is that those changes can't happen. And that's not necessarily appropriate, particularly as we move further and further away from that base period. Now, there is a solution to this, and I don't want to go into detail because the calculation is actually quite complicated. But if you were to look up the real GDP figures in your national statistical agencies' databases, you'll find probably a reference to what's called a chain volume index. Now, what a chain volume index does, and it's actually a fairly complicated calculation, is it moves that base forward year by year, so that each year you're valuing that year's quantities using the prices from the previous year. So you're never getting too far away from the base period. Essentially, you're updating the base period each period, moving it forward by 1 year. Now, for our purposes, we don't have to worry about that too much. It's not going to change anything that we do. The concept of real GDP, however, both as I've described it, but also using this chain volume index, that concept is essentially the same. That what we do with real GDP is we want to take price changes out of the calculation so that when we see a change in real GDP, we know we're looking at a quantity change only. One important refinement about GDP, and this relates to unsold inventory. You may already have been wondering how this is handled, because after all, I've been talking a lot about how there is an equivalence between production and expenditure, which makes it sound as if each and every period, whatever is produced is actually purchased. But of course, that's not necessarily the case. It's often the case that firms will produce a certain amount of output in a period, but not necessarily sell all of it, and this gives rise to unsold inventory. Well, if there's unsold inventory, how is it possible for production and expenditure to give the same value for GDP? Well, it's actually not as big a problem as you might think, and it goes back to this notion of investment, of firms' investment being a type of expenditure in the economy. Remember, investment is all about an expenditure that happens in the present, but which meets a future need. Now think about unsold inventories. Unsold inventories are kept by firms precisely because they meet a future need. They're available to meet, let's say, an unexpected increase in demand in the future. So unsold inventories can be thought of as being a form of investment by the firm. So let me give you just a very simple example to show how all this works. Let's take the month of December 2012, and suppose in the economy there's been a flow of production equal to $1 billion, but over that month expenditure has fallen short. Expenditure is only 0.8 billion, meaning that firms have accumulated a change in inventories of $0.2 billion, essentially unsold stock. Now, what we're going to do is as follows. We're going to take that 0.2 billion and recognise that firms are hanging on to those inventories to meet this future need, the possibility of being able to sell it in the future, and we're going to say that that is going to be equal to a part of firms' investment expenditure. So once you think about unsold inventories like that, what we actually have in this economy is production giving us a flow of $1 billion will in fact be equal to expenditure if we take expenditure as being that 0.8 billion and add to it the investment expenditure of firms in the form of inventory investment. So once we recognise inventory as part of investment, then even if not everything gets sold in a period, that equivalence between production and expenditure is still maintained. Well, let's suppose something different happens in the following month, January 2013. Once again, over that month, there's a flow of production equal to $1 billion. Well, let's suppose there's an increase in expenditure, $1.2 billion now. How is this even possible? It's possible because that unsold inventory is now being sold. So there will be a change in inventories, but it won't be adding to inventories, it'll be taking away. And so we record the change in inventories in this case as minus 0.2 billion. But again, this is going to be part of investment, but it's going to be negative investment. So what we have in this month, once again, there's a flow of production equal to 1 billion. And this is going to be equivalent to expenditure because whilst we have this $1.2 billion of expenditure, we record the fall in inventories as negative investment. So we subtract the 0.2, and so once again we have this equivalence between production and expenditure. So we've done a lot in this lecture, but it's all going to be useful for us as we go through this course in macroeconomics. A lot of what we've done revolves around what is called the national income accounting identity, which is this idea that production, expenditure and income are actually three different words that mean exactly the same thing, and that is gross domestic product. And you'll soon get used to this idea, and you'll actually hear me in these lectures use those three terms interchangeably. Sometimes I'll talk about production, sometimes I'll talk about expenditure, sometimes I'll talk about income. It doesn't really matter which word I use, it all means GDP. And over the course of this subject, you will actually see how that national income accounting identity is used over and over and over again as we explore issues in macroeconomics. The other thing I want you to take away from this lecture is this notion that we often divide the economy into distinct sectors. We have our household sector. Now I'm just going to focus on expenditure here, but there's income flows going to all of these sectors as well. Our household sector is responsible for consumption spending, and given our assumptions, total consumption spending is spending on domestically produced goods and services and imports. Our firms, their expenditure is investment, plant, equipment, and inventory investment, changes in inventories. Our government is involved in expenditure. We'll just record that as G, and the foreign sector is involved here through its purchases of exports. As I said at the very outset of this lecture, a lot of macroeconomics is essentially trying to understand what is happening to gross domestic product. It's unlikely that we will have many lectures in this course where we're not talking, and often talking a lot, about gross domestic product. It is probably, certainly, the key macroeconomic performance indicator. The importance of GDP as an indicator of macroeconomic performance is highlighted in this chart. This shows the growth rate of GDP, how GDP has changed from year to year. And it's dominated by the global financial crisis. And this shows you the magnitude of the global financial crisis, what it meant for economies all over the world was a significant fall in gross domestic product. In other words, these economies shrank during the global financial crisis. The flow of economic activity contracted, and as you can see from this chart, contracted dramatically. All sorts of consequences flow from that observation that we're going to explore in this course. But gross domestic product is probably the key indicator of macroeconomic performance. And when something like the global financial crisis hits, fortunately that doesn't happen too often, the severity of the crisis in terms of what it means for macroeconomic performance is pretty stark when you start looking at what it means for gross domestic product. And even looking here, we can see Europe heading into negative territory, Japan perhaps also. A lot of our work will be understanding what is going on with gross domestic product. And it's true, and I've been emphasising that macroeconomists focus on gross domestic product a lot, and I think you can see why that's the case. As an indicator of macroeconomic performance, it's pretty hard to go past GDP. But I want to end this lecture looking at a broader question, and actually a question where there is a lot of debate and soul-searching that takes place in economics. This is the question of whether gross domestic product is anything more than an indicator of macroeconomic performance. Does it tell us anything about broader social welfare? This is something a lot of people and a lot of economists worry a great deal about. We spend so much of our time focusing on gross domestic product. Is this actually the right thing that we should be focusing on? One way of posing that question is the following. Is it necessarily the case that growing a nation's gross domestic product actually makes the citizens of that nation any happier? And there is actually a really exciting branch of economics that's developed in recent years looking at this question, known as the economics of happiness. Ultimately, the end result of all of this economic activity, one would like to think, is an improvement in people's welfare, an improvement in their life satisfaction, an improvement in their level of happiness. It turns out that this is a surprisingly controversial area in economics. The chart you're looking at has become very, very famous. It shows two lines going back to the 1970s, and this is data for the United States. The dashed line shows what's called real income per capita. This is just measured looking at United States real GDP per person, or if you like, on average, how much income do people in the United States have? And you can see from the chart that this has been trending upwards. So at the end of this period, average incomes in the United States significantly higher than they were at the beginning of this period. That's what we call economic growth. The other line on the chart, the solid line, the line labelled happiness, shows the results from a survey taken at regular intervals of a sample of the United States population, which simply asks people to rate their happiness. And you can see that it jumps up and down a little bit, but there's no long-run trend. On average, at the end of this period, people in the United States were about as happy as they were at the beginning of this period. So we have a bit of a conundrum in some sense. We have rising incomes, but not rising happiness. And a great many people have looked at this chart and come to the conclusion, well, we're actually, as economists, as macroeconomists, focusing on the wrong thing. Why are we trying to grow nations' GDP if it in fact is not making people any happier? Now, there's an enormous amount of research in this area trying to interpret this result and come up with an answer to that question. As you can imagine, it's a pretty controversial area. I want to make a couple of observations about this. The first observation is that there are certainly a number of aspects of the quality of life which do, in some fundamental way, seem to be related to what is happening to gross domestic product. We know, for example, that the quality of health care is often higher in those countries that have higher levels of GDP. And as a consequence, longevity, the amount of time that people can be expected to live, is often higher in those countries with higher GDP. Simply looking at this happiness graph shouldn't, I think, lead one to throw the concept of GDP out the window and say, well, it's not really that important. There is simply too much that affects people's welfare that does seem to be positively related with GDP. The other observation I want to make, and this is another famous chart, is that whilst something might be true for an advanced economy like the United States, doesn't necessarily make it true always. This is a really interesting piece of research which essentially looks again at this relationship between income and happiness, but does it for a group of people whose circumstances changed quite dramatically. This analysis was conducted on the citizens of the former East Germany, and it covers the period of reunification. Now, obviously, an enormous amount happened to those people as a result of the bringing together of the two Germanys. But one of the things that happened was a pretty dramatic increase in their average levels of income. And for those people, the research shows that that did coincide with an increase in their happiness. And so it may be that if we're just thinking about happiness per se, that if you take people whose incomes are relatively low and bring those incomes up to the level of other people, comparable people perhaps, maybe that does matter for happiness. So I think as macroeconomists we have a lot of work to do to really understand this link between GDP and happiness. I do know that looking at GDP, as we will in this course, is an extremely powerful way of thinking about macroeconomic performance, but I guess we shouldn't necessarily conclude that GDP is the be-all and end-all of human welfare, though I will defend the proposition that it is an important aspect of human welfare. In this lecture, we're going to begin our exploration of long-run economic growth. And we're going to look at some key characteristics of economic growth over the very long run. And then we'll start exploring some of the key ideas macroeconomists have developed to try to understand both the reasons for long-run growth and why it is that different countries, different economies have had different experiences in terms of their economic growth. Why is it that some countries have grown fairly steadily over 100, 200, 250 years, whilst other countries have not enjoyed that economic growth? This is actually one of the really big areas in macroeconomics. Indeed, some of the most exciting developments in recent macroeconomics have involved economic growth, though the study of economic growth is probably one of the oldest parts of the entire discipline of economics. What I want to do in this part of our course is introduce you to some of the key basic fundamental ideas that macroeconomists have found useful to improve their understanding of economic growth. But please be aware that there have been a whole lot of exciting recent developments in this area that have enabled us, I think, to have a pretty good understanding of what really matters for economic growth. But these recent developments have all built on the basic fundamental ideas that we'll cover in this course. And I think you'll find that the ideas that we go through in these lectures enable us to get quite a long way to understanding what are the basic fundamental forces responsible for long-run economic growth. So let's begin with a very important observation. And the observation is this: what you're looking at is gross domestic product per capita for the United States. Very long-run data, indeed, going back to the 1870s. Per capita simply means we're looking at the average flow of GDP per person in the economy. And for industrialised countries, the sort of pattern you're seeing here is fairly typical, where there is a tendency over the long run for the flow of GDP per person to grow, but to grow in a particular way. What you're looking at is known as exponential growth. And an economic variable that has this exponential growth characteristic is one that has this curved growth through time. As you can see, it's not smooth. There are periods where here, the Great Depression of the 1930s, where there was a very serious interruption to growth, and in our work on business cycles to come in later lectures, we'll investigate some of the ideas macroeconomists have developed to explain periods like that. And of course, this is an extraordinary period which represents the incredible increase in production and hence GDP that occurred during the wartime years. I just want to talk a little bit about the nature of exponential growth because there's something quite intriguing about what you're seeing here, but it isn't immediately obvious unless we really delve into the very nature of exponential growth. And I'm going to resort to a little bit of mathematics now. Now, you don't need a lot of heavy-duty mathematics to progress in this course, and I'm not expecting you to have a detailed knowledge of the sorts of techniques I'm going to show you. Some of you will, recall what I'm about to show you from your high school maths, but it's not important for you to work through the maths necessarily, as long as you understand the basic idea that I'm going to convey through the use of this mathematical discussion of exponential growth. So let me explain. What we're interested in is this variable here. I'm using Y as my notation for gross domestic product, for real gross domestic product. And the subscript T simply means I'm referring to GDP in a particular time period T. So it might be the year 2010, for example. A variable that grows exponentially can be represented using the following formula. The value for GDP in period T can be related to the value of GDP at some initial period, and we'll call that initial period Y0. So that might be here, for example, 1870. And the way we represent exponential growth is as follows. We take that initial value for GDP, multiply it by the following, 1 plus, I'm going to use the Greek letter alpha there to represent the economy's annual growth rate. Alpha, for example, might be a number like 0.02, which would represent an annual growth rate of 2% a year. It turns out that's actually a pretty accurate figure for the United States. But alpha, of course, will differ for different countries. So it's a small number, 0.02 would be a typical number. That's the number for the United States. It represents an annual growth in real per capita GDP of 2% a year. Now, the characteristic of a variable that's growing exponentially is that we take that growth rate, we add to it 1, and then we raise it to the power t. So this is a little mathematical representation that corresponds to this exponential growth that we see in the long-run GDP data. As I said previously, alpha, which is the annual growth rate for the United States, is around 2%. In terms of the actual formula, the way we would represent that is alpha equals 0.02. So what's interesting about that? Let's take that exponential growth formula and manipulate it a little bit. So in any period t, given that GDP is growing exponentially, that can be related to its initial value multiplied by 1 plus the growth rate raised to the power t. Now that's true in general. If it's true in period t, it must also be true in the previous period. So if this first equation relates to the year 2010, then in the year 29 we must also be able to write that the value for GDP in that year is also related to whatever its initial value was, again multiplied by 1 plus that growth rate, but now instead of being raised to the value t, because we're talking about the previous period, that is raised to the value t minus 1. All right, so why am I doing that? When working with variables that grow exponentially, it's often useful to transform the variable into natural logs, and ln is the standard mathematical notation to represent natural log. Again, this will be familiar to many of you from your high school mathematics, but if this is not familiar to you, I'm not expecting you to necessarily understand all the details of the mathematics, but we are going to demonstrate a very important point about long-run economic growth that can really only be explained if I go through this maths, but it's really the point we're getting to that I want you to focus on. But we do have a little bit of work to get there. Now, if I take the natural logarithm of the value of GDP in period t, I can write that as follows. It will be equal to the natural logarithm of the initial value of GDP, y0, plus t times by the natural logarithm of 1 plus alpha. Now, this term here, as long as alpha is a small number and our 2% growth rate, or alpha equal to 0.02, would be considered a small number, but it turns out that there's a very convenient mathematical approximation we can make. The natural log of 1 plus a small number turns out to be approximately equal to that small number itself. And if you have a calculator handy, you might want to just punch some numbers in and check that for yourself. Which means we can rewrite this expression as the natural log of the initial value plus T times alpha. Now, I can do exactly the same transformation with the previous value for GDP, which will give me the natural log of the initial value of GDP plus, not T, but T minus 1 now, multiplied by alpha. Now, none of this necessarily looks all that helpful at this stage, but have a look what happens if I do the following. If I take the natural log of the value of GDP in period T and subtract from it the natural log of the value of GDP in the previous period, what I'm actually doing is subtracting those two expressions. When I do that, the initial values drop out, and I'm going to be left with T times alpha minus T times alpha plus alpha. All I've done is taken those two expressions and subtracted the bottom one from the top one. That gives me alpha. So what is this telling me? It's telling me if I take the natural log of GDP and then take the difference between one period and the previous period, that difference gives me the growth rate, alpha. Now, why is that interesting? What you're looking at here now is our graph of per capita GDP, but this time I've taken the logarithm of GDP, the natural logarithm. And you can see that it no longer has that curved exponential shape, but it now looks much more like a straight line. And that's really important. The slope of that straight line is going to equal the growth rate. And apart from some very unusual historical experiences, most notably the Great Depression, the wartime years, and perhaps even the most recent observations associated with the global financial crisis, what you can see is that for the United States, the growth rate of the economy has been fairly constant over this very, very long period of time. For example, over here, the 1960s to the 1980s, when you look at the data as we have in this graph, it doesn't look all that different to what we saw in the 1880s, 1890s, 1900s. And what macroeconomists have concluded from this is that in the study of long-run economic growth, there are some key fundamental long-run forces at work which probably are acting in pretty much the same way in recent periods as they were some 100, 150 years ago. In other words, it might very well be the case that there are truly some key fundamental, deep structural aspects of an industrial economy that are driving economic growth in some very fundamental sense and are doing so in pretty much the same way today as was the case some 100 years ago. Now, obviously, some of the details are going to be quite different. Technology is very different, for example, but you'll actually see that technology itself is one of these really important fundamental structural forces. So let me explore this a little bit. In the study of economic growth, ultimately what we're trying to explain is this: real GDP per capita. Now, we know from the work we did on GDP that GDP itself is a very complex measure of economic activity, and it has this extraordinary characteristic of representing three things simultaneously: production, income, and expenditure. Think about it as income for what we're about to do. And then it starts to make sense why we focus on real GDP per capita as our measure of long-run economic growth. What we're ultimately trying to understand is what determines the average flow of income per person in the economy. So our analysis of GDP in this instance is very much a story about trying to understand the income that is available per person in the economy. Now, real GDP per capita is simply defined as the flow of GDP Y divided by the population. Turns out that just working with this gives us some pretty profound insights into the nature of economic growth and what some of these fundamental sources of growth might be. To explain this, I want to introduce a new piece of notation, the letter capital N. Now, the letter capital N, I'm going to use to denote the labour force in the economy. So the total amount of labour that is available to produce the output in the economy. Now, why is that useful? Take our real GDP per capita, and now I'm going to do what is a fairly basic mathematical trick, but it's actually going to provide us with extraordinary insight, because I'm going to write that real per capita GDP in a slightly different but nonetheless equivalent way. So take real GDP and divide it not by population but by the labour force. Multiply that by the labour force divided by the population. Now, you can see that I've really not done anything at all, because the labour force on the numerator here and the labour force on the denominator there will simply cancel each other out. So on the right-hand side, all I've done is written real per capita GDP exactly the same as on the left-hand side. But I've broken it up in a particular way to highlight what macroeconomists believe are the two fundamental sources that ultimately are responsible for economic growth. Let's take this one first, Y divided by the labour force. What that represents is the average amount of GDP, the average amount of aggregate production produced per worker. And the term that economists give for that is average productivity. On average, how much does each worker in the economy produce? And that's what we mean by average productivity. This term, N divided by the population, you can almost think of that as a demographic variable. It's representing the proportion of the nation's population that are actively engaged in productive work. So what proportion of your population is in the labour force? In the labour force meaning actively contributing to the production of GDP. And so what we're actually looking at here is something pretty profound. It's an insight that says, at a very deep fundamental structural level, if you want to understand what is determining the average amount of real GDP per person, the average income per person in the economy, it's going to be as a result of the interaction of two very important economic variables. The first, average productivity, how much output can each person in the labour force produce, and secondly, how many people do you actually have producing output? So at a very, very sort of basic level, average productivity is how well are your workers able to produce output, and the proportion of the population working is how many workers do you have available to produce output. And all of the explanations that macroeconomists look at to explain long-run economic growth, including the ones that we are going to be focusing on in our course, essentially focus on either one or other, and sometimes both, of those two fundamental factors. Most attention is directed to this one, average productivity. And there's been a lot of empirical work that suggests that that's probably the most important of these two factors. But this is not to neglect demographic factors, though in the theories of economic growth that we're going to consider, our focus is very much going to be on average productivity. So let's begin constructing those theories. And I'm going to start with a very important concept, the concept of the production function. And almost all, actually probably all, economic models of economic growth start with this very, very important analytical device. As you'll see, when we speak of the production function, what we're talking about is a very simple representation of something that in reality is incredibly complex. That is, how do firms bring together factors of production in order to produce output? It's a really very fundamental, basic way of thinking about what a firm is. A firm is an organisation that exists in order to bring together various factors of production, and in doing so, to produce output. And we're going to deal with very simple production functions. As a lot of economics is, it's a very simplified view of reality. But remember that when we simplify things down in economics, what we're doing is really trying to get at what are the key basic fundamental forces at work. So a very basic production function consists of two factors of production only. Labour, so that's you and I, workers, and capital. Now, capital is one of those words that economists use in a very precise way, and it's not necessarily the same way that non-economists use it. When I speak of capital, I'm talking about the plant and equipment, the machinery, if you like, and the factories, the physical, tangible infrastructure and equipment that firms use in order to produce output. And you can think of a firm as bringing together these two factors of production, combining workers with capital, or combining capital with workers. The two are very closely intertwined in order to produce output. Labour and capital collectively are often known as the primary factors of production. They are, of course, not the only factors of production that influence firms' ability to produce output. There are a whole range of what we will call secondary factors of production. And secondary factors of production comprise anything other than labour and capital that influence firms' ability to produce output. Examples might be technology, not just the machines that are available to firms, but how good are those machines? What is the level of technology that is embedded in those machines? Or it could be the skills of the workers. That would be another secondary factor of production. A firm may have 100 workers available to it, but the amount of output that can be produced using those 100 workers may differ according to their skill level. It might be the climate of the region in which the firm is located may have an influence on how much production can be achieved. It could be anything at all. So secondary factors of production, it's not possible for me to write down a list of those secondary factors of production because it literally encompasses anything and everything other than the primary factors that influences output. So we're going to delve into much more detail about the production function, but please don't lose sight of the fact that it's really a very simple concept, a very sort of gross simplification of something that is extraordinarily complex, how firms produce output. It's very much based on this idea that firms exist to bring factors of production together and in doing so produces output. Our focus will often be on these primary factors of production, but you'll see that the secondary factors also have a very important role to play. What you're looking at here is something known as a production table. A production table is one way of representing this idea of a production function. In a production table, what we do is essentially conduct an experiment where we vary the amounts of labour and capital whilst holding any and all secondary factors of production unchanged, and then we record what happens to the output that can be produced. So just to repeat, a production table, we vary the amounts of labour and capital available to the firm, we hold all secondary factors of production constant, and then we record how much output is then produced. In this example of the production table, I'm conducting a very specific experiment. Here, I'm holding not only the secondary factors of production constant, but I'm also holding the amount of labour constant. And then I'm going to vary the amount of capital that the firm has, starting with 1 unit of capital, through to 2, through to 3, 4, 5 and 6, and then record how much output is then produced. So here I'm going to hold labour fixed. I'm certainly holding the secondary factors fixed as well. And I'm going to vary capital. Now it's conventional in macroeconomics to use the letter K as our symbol for capital. And I want you to look at those numbers and look at them very carefully because they are consistent with a characteristic of real-world production functions that we often observe. This is a characteristic known as diminishing marginal productivity. In this case, because it's capital I'm talking about, we would talk about the diminishing marginal productivity of capital. What does this mean? Suppose we start with capital equal to 2, so we have 2 units of capital, and then we vary it. We increase it to 3 units of capital. From the table, you can see that there will be a change, and I'll use the Greek letter capital delta, it's my shorthand notation for change, there's going to be a change in GDP in this case equal to 0.83. You can see that from here. So we've increased capital and we've gotten some more output. In fact, we've gotten 0.83 extra output. If you repeat this exercise, this time starting from k equaling 3 and moving from k equal to 4, then from the table you can see that, yes, once again, output does change. Changes by 0.54. And compare those two numbers and you'll see what we mean by diminishing marginal productivity of capital. The extra output that has been produced as a result of growing capital from 3 to 4 is smaller than the extra output that was produced when we grew capital from 2 to 3. And if you repeat this exercise, you'll see that that is a general characteristic of these numbers. That as we grow capital, holding labour fixed and holding all of those secondary factors fixed, we do get extra output, but we're getting a diminishing amount of extra output. What's the intuition behind that? Well, think about it. Think about if you were this one worker. You're quite productive when you get your one machine, but then if you suddenly have 2 machines available, yes, you can produce more output, but it's going to be not necessarily that easy for you. You have to rush from one machine to the other machine, and so the amount of extra output you get from having that second machine is not as great as the extra output you were able to produce when you got that first machine. Then you're given a third machine. You've now got 3 machines to keep operating. You're running from one machine to the second machine to the third machine. Yeah, you're going to get some extra output, but you're probably not going to get that much extra output from the third machine, and so on and so forth. So diminishing marginal productivity of capital with a fixed amount of labour, adding to the amount of capital that is available gets you more output, but diminishing in the sense that we're getting smaller and smaller increases to that output. So let me just summarise, because I introduced a few terms there that I just want to make sure that we well and truly understand. You'll hear economists talk a lot about the marginal product. The marginal product always relates to a particular factor of production, in this case the marginal product of capital. What it represents is the extra product or the extra GDP resulting from a small increase in capital. And we usually think about it as a 1 unit increase in capital. How much extra output do you get from that additional unit of capital? When we speak of diminishing marginal product of capital, what we're essentially saying is the marginal product of capital, and I'll now use the shorthand notation MPK for marginal product of capital, declines as the amount of capital increases. Please don't get confused about this. We are still getting more output. It's just the extra output we're getting, the extra product we're getting, is diminishing as we increase the capital stock, remembering throughout all this, and this is crucial, we're holding labour fixed and we're holding all of those secondary factors fixed as well. The only thing that is varying here is capital. Now I'm going into this into some detail because you'll see as we progress through this material that this concept of diminishing marginal product of capital is actually hugely important in some of the most important theoretical models of economic growth that macroeconomists have developed. We're going to see that this characteristic of production actually has some very profound implications for the very nature of economic growth. All right, so that's diminishing marginal product of capital. The second characteristic of production functions, indeed the second characteristic of production in the real world that we observe, is also a diminishing marginal productivity concept, but in this case it relates to labour. So there is, in the real world, a characteristic of production known as the diminishing marginal productivity of labour. And I'll use capital L now for labour. And this production table illustrates it, and I'll leave it to you to work through. What I've done in this table is I'm holding capital constant at 2 units of capital, and then I'm varying labour from 1 to 2 to 3 to 4, recording the amount of production each time. Check for yourself that this indeed is consistent with diminishing marginal productivity. We are getting more output from increasing labour, but the amount of extra output we're getting is diminishing. Now for our third characteristic of real-world production, if you like, the third characteristic that any production function we work with should be able to represent. This is quite different, this third characteristic, from the diminishing marginal productivity of capital and diminishing marginal productivity of labour. In this third characteristic, what I'm doing is now varying both labour and capital. The only thing I'm holding constant here are those secondary factors of production. And so I've been able, by doing this, by varying labour and capital, simultaneously, I can, as you can see, complete the whole production table. So for all combinations of labour and capital, here I've recorded the resulting output. And I want you to focus on these numbers here, because these numbers show something quite profound. So the first number represents what happens when I have 1 unit of labour, 1 unit of capital. The second number, I now have 2 units of labour, 2 units of capital. Third number, 3 units of labour, 3 units of capital, and then 4 and 4. And I want you to look at those numbers in red and see if you notice something. What you're looking at is a characteristic of production known as constant returns to scale. And constant returns to scale is an observation about production that says the following. If we scale up the amount of labour and capital by the same factor, you're going to get exactly the same scaling up of production. Now, we often use the Greek letter lambda to represent that factor. For example, when I write lambda equals 2, what I'm actually saying is I'm going to take an amount of labour and an amount of capital, and simultaneously I'm going to double both of those primary factors. So that's like going from 1 to 2. 1 unit of labour to 2 units of labour, 1 unit of capital to 2 units of capital. And have a look at those two numbers. I get exactly twice the amount of output. And that's what we mean by constant returns to scale. If I scale up both factors of production by the same scaling factor, in this case 2, I'm going to get exactly the same scaling up of production. Same thing happens when I go to 3 and 3. I'm now getting 3 times the production that I had when I had just 1 unit of labour and 1 unit of capital. So constant returns to scale is an important characteristic of production in the real world. It doesn't hold always, but it holds often. And we often embed this concept in our formal models of the production function. So let me just give that just a little bit more structure for you, because this is a concept that is going to be very important for us. So CRS is my notation for constant returns to scale. And here's a formal definition of it. If both capital and labour, and please remember that this is different from that diminishing marginal productivity where we held one of those factors fixed. Here we're varying both primary factors, but again, I won't write it down, but please be aware that we're holding secondary factors constant through this. If both labour and capital are scaled up, let's write it like this, by some multiple or some factor, and I'll use the Greek letter lambda as my shorthand notation for that factor. The implication of that is we will get exactly lambda times the output. For example, lambda equals 4. You're going to get 4 times the output after we've quadrupled the amount of capital and the amount of labour. All right, this has all been a bit abstract, so I'd certainly like to emphasise that we are talking about real-world events here. We are talking about firms and their combination of factors to produce output, but I am aware that it is a little abstract when you see it like this. And for those of you who are unfamiliar with economic models, it does take a bit of time to get used to making the bridge between the abstract way we write down these concepts and what's happening in the real world. But as I keep emphasising, we see this going on around us all the time, firms bringing together factors of production to produce output. One useful way of thinking about what we're seeing here is to move away from the production table, which is a bit cumbersome to work with, and instead illustrate visually what's going on. So what you're looking at here is another way of representing a production function using what's called a surface chart. So it's a three-dimensional plot of this concept of the production function. And so what we're doing here, similar to our last production table, is as we move along this axis, we're varying the amount of capital. As we move along this axis, we're varying the amount of labour. And then the height of this surface is giving us the amount of output. Let me just explore that a little bit more, because I'm going to come back to this surface chart and show you something really important very, very shortly. But to do that, I want to introduce you to the mathematical representation of the production function. You can see that in the centre of this slide. Most of what you're looking at is going to be fairly familiar to you, with one exception. So on the left-hand side, lowercase y represents real gross domestic product. On the right-hand side, capital and labour. I'm using lowercase letters because there's a convention in macroeconomics to use lowercase letters when we're talking about real variables. So capital and labour are primary factors of production influence or help to determine the total amount of output. The F here is just represents function. So what I'm saying here is the flow of output that the firm produces is a function of the primary factors of production. So function means bringing together, combining. That leaves one part of that expression that I haven't talked about yet, and that's capital A. Capital A it's a number. And the value of that number represents all of those secondary factors, or if you like, represents the combined influence of all of those secondary factors of production. It's everything that could possibly influence firms' ability to produce output other than capital and labour is represented in summary form by the value of A. So what you're looking at here is actually a very rich way of thinking about firms' production. Firms exist to bring together the primary factors of production in order to produce output. It's not just the total amounts of the primary factors that influence firms' ability to produce output. Firms' ability to produce output is also going to be influenced by all of these secondary factors of production. And remember, this could be anything at all that influences production, like technology, like skills, like climate. I'm sure you can think of a great many other things. What this means is that you may have two firms, or indeed two economies, that have equivalent amounts of capital and labour, but their ability to produce output may still be different if the secondary factors of production, or as these are sometimes also known, I might as well introduce the term now, total factor productivity is another term for these secondary factors. If total factor productivity or these secondary factors differ, then the same amounts of capital and labour can yield different amounts of output. And if we go to this surface chart, we can illustrate that very nicely. What I've done to construct this surface chart is to take a value of total factor productivity equal to 2. Should I vary that, for example, should it fall to 1.4, you can see that the production surface shifts down. And that's exactly what's the whole point about total factor productivity. The same combinations of capital and labour are now producing less output because there has been a fall in these secondary factors of production. That's how it looks when we have 2. That's how it looks when we have 1.4. The height of the production surface is itself changing. And so the theory that we're about to explore over the next little bit of our course is going to bring all this discussion together in a much more systematic way. We're going to bring together this idea of the production function. We're going to bring together these characteristics of the production function: constant returns to scale, diminishing marginal productivity. We're going to bring in the effect that changing total factor productivity can have, and we're going to do it all in a very systematic framework that will enable us to say some very, very profound things about the very nature of long-run economic growth. All right, so here we have the three-dimensional representation of the production function. There's an enormous amount of detail on this kind of three-dimensional graph. We're taking all possible combinations of labour and capital, and we're seeing what the corresponding levels of output will be. Now, whilst we have a lot of information in this graph, it's actually very cumbersome to work with these three-dimensional surfaces. And so we often make a simplification to the way we visually represent the production process or the production function, a way that enables us to very quickly start learning about some profound key structural forces that underlie the entire process of economic growth. And we achieve this by doing the following. I'm going to work, for the time being, under the following set of circumstances, where I'm going to hold the amount of labour and also the amount of total factor productivity fixed, unchanging. Now we'll change that shortly, but for the moment let's just assume that we're looking at a production process where there's a fixed amount of labour and where total factor productivity is not changing. And that all we do is map or graph what happens to output when we vary capital. When we do that, we no longer have to work in this three-dimension space. We can work in 2 dimensions only and use what is called the two-dimensional production function. So remember, we're holding labour and total factor productivity fixed, and we're looking at what happens to output when we vary capital. And there are 2 key characteristics of this experiment that this graphical approach, this two-dimensional production function, really nicely captures. First, and I guess most obviously, what we are able to represent here is the idea that as you provide more capital to the production process, the implication of that is more output can then be derived. Second, however, is this concept of the diminishing marginal productivity of capital. That as the amount of capital increases, the marginal product of capital, the extra output that we get, falls. So we still are getting extra output, but you're getting smaller increases of output the more capital you have. And that is illustrated very nicely by the following. So here we have increased the amount of capital, and then we can read off the vertical axis how much extra output is the result. If we repeat that experiment but down the right-hand side of the horizontal axis, where we start already with a high level of capital and add a bit more capital, well, you can see that the increase in output we get is much smaller. So it is the curved shape of the production function that is reflecting the diminishing marginal productivity of capital. There are other things we can illustrate on this diagram that are going to be very useful for us. Let's think about the following experiment. And the experiment is this. This time I want to show you how the two-dimensional production function can be used to illustrate the following circumstance, where we hold labour and capital fixed. This time I'm going to increase total factor productivity. We saw with our three-dimensional production function that what an increase in total factor productivity did was to shift the surface of that production function upwards. In 2 dimensions, it's actually a similar sort of concept. So we're going to hold capital fixed at some level, and behind the scenes we're not changing labour either. If we increase total factor productivity, holding capital and labour unchanged, well, that increase in total factor productivity itself should be sufficient to generate us some extra output. Think of it as an improvement in technology, for example, or work practices, or the skill of labour. Any of those sorts of factors, should they increase, are likely to result in more output. So we can illustrate that by an upward shift of this production function. We haven't changed capital, as you can see, nor have we changed labour, but the increase in total factor productivity is sufficient to generate more output. So even though it's a very simple representation, 2 dimensions, not even 3 dimensions, there's still a lot of detail here. We've been able to capture the fact that more capital means more output. We've been able to capture the fact that there is a diminishing marginal productivity associated with capital. And we've also been able to capture the fact that should total factor productivity improve, then we can also represent what that implies for output. So it's a very, very simple analytical tool that conveys an enormous amount of information. Information we're going to exploit as we delve behind the scenes of economic growth. There's one more refinement to the analysis I'm going to make, and that is to work with what is called the per capita production function. You'll remember that when we think about economic growth, what we're ultimately trying to explain is what is happening to per capita aggregate income in the economy, the average amount of income per person. So I want to work with a notion of production function that is also in per capita terms, that relates to the production process from the viewpoint of, if you like, an average worker in the economy. And I'm going to do that by making a very simple assumption, which is going to enable us to work in per capita terms very conveniently. And this is to assume that everybody in the population works. Now, I don't have to assume that for this analysis that we're going to go through, but it absolutely makes things much, much simpler to show without actually adding any complications that we would necessarily have to be concerned about. So if we assume the entire population works and then measure on the vertical axis not just output as we did previously, but this time output per worker. So in that expression I have L. Now, L now is the notation I'll use for my labour force. So what I have on that left-hand side is per capita output, or per worker output, I should probably say. But given that everybody in the population works, what I have in fact there, remembering that output and income are exactly the same things, is I have a measure of per capita income. And that's what the analysis of economic growth is designed to explain or understand. What are the key factors or forces at work that determine per capita income? On the horizontal axis, I have the amount of capital relative to the number of workers. That is known as the capital labour ratio. Think of this as the average amount of capital that is available to a worker when they turn up for work. So here we have the production function per capita terms. We have per capita output, which is the same as per capita income on the vertical axis, and the capital labour ratio, the amount of capital available in the economy per person, on the horizontal axis. Note that by working with this per capita production function, we are very much focusing the analysis on average productivity. You'll recall from earlier that we can decompose real GDP into 2 sets of factors, one relating to average productivity, the second relating to the proportion of the population who work. But if we make this assumption that everybody works, then the only factor that really matters is therefore average productivity. And indeed, that's what we're measuring on this vertical axis, the amount of output per person who works. And so by working with this per capita production function, the focus of the analysis very much becomes a story about average productivity. And that's probably the best way to think about how we're going to proceed. So it's going to have similar characteristics to what we had previously. So that now, if we increase not capital on its own, but the amount of capital per person, if we increase the capital labour ratio, that by itself will be sufficient to generate higher average productivity or to generate higher per capita income. So that increasing the capital labour ratio, providing each worker with more capital, in other words, is a path to economic growth. It increases the flow of per capita income. But there's an alternate path to growth, and the alternate path to growth is through growth in total factor productivity. And as before, that can be represented by an upward shift, this time in the per capita production function. This simple concept of the two-dimensional per capita production function will already enable us to say some important things about the process of economic growth. I'm going to explore two implications, and these implications will turn out to be very important to economists' story about what ultimately really matters for economic growth. So implication number one relates to that idea of the diminishing, which I'll just abbreviate to DIM, the diminishing marginal productivity of capital. Strictly speaking, in this case, the diminishing marginal productivity of providing more capital per person. Suppose we did exactly that, starting with a relatively low amount of capital per person. You could think of this as an economy starting its process of economic growth from a relatively low base. It started not having that much capital per person, and we provide that economy with some extra capital. What you can see is that that yields quite significant amount of economic growth. But if you were to repeat that exercise for an economy that already had a high capital labour ratio, and a more mature economy, if you like, that has already experienced significant economic growth and has built up a lot of capital per person over the years. If you were to provide such an economy with extra capital per person, you will get more per capita income, but not that much more. And this is a direct implication of diminishing marginal productivity of capital. Providing more capital per person is an effective strategy for promoting large-scale economic growth if you're dealing with an economy that doesn't already have a lot of capital. If you have an economy that already has a lot of capital, then providing even more capital is actually not going to yield much in the way of economic growth. The second implication relates to that second path to economic growth, the increase in total factor productivity. Suppose we did this for an economy that had a relatively low capital labour ratio. once again, you'll get some economic growth by improving total factor productivity, increasing the level of technology, for example, or the skill level of the labour force, perhaps improving the transport system. Any of those non-capital labour factors that influence growth, well, even if you have a low capital labour ratio, that's going to get you some more per capita income. But not as much of an increase relative to the economy that already has a high capital labour ratio. Here we get a higher increase in per capita income than in that first case. And these two implications are a very important lesson about the process of economic growth, namely that the road to economic growth, the path to economic growth, if you like, can be very different for economies at different stages of their development. An economy that is beginning economic growth, that is starting with a low amount of capital per person, then the most effective way of boosting per capita incomes is not through total factor productivity improvements, though that will help, it's through growing the capital stock. An economy that is more mature, that has had a longer history of economic growth, that has already built up its capital labour ratio, if it wishes to experience even more growth, then diminishing marginal productivity means that there's not much to be gained by further growth in the capital stock. Growth in that case is going to rely on growth in total factor productivity. What matters for growth is different across different economies.